let's start by just remembering some exponential rules.
No, we'll do that in a second. So, here are the things that we'll fill in as we progress, and one of them you already know. What's the log base b of 1? 0. Because b to the power 0 equals 1. The log of 1 is 0. There's one fact you already know about logarithms. We'll develop some other ones. We'll develop a rule that says what the logarithm of a product is. We'll develop a rule that says what the log of a quotient is and what the log of an exponent is. And that's going to be our fourth goal in today. And the way that we'll get that is we'll study some corresponding rules about exponentials. So here are some rules we know about exponentials. For any base b, what's b to the power 0? Yeah, but through the mask it's hard to hear you, so say it louder. 1, yeah. Right, you already knew that, but yeah. For any exponents x and y, what is b to the x times b to the y? Almost? Yeah. Right, for the reason that like 2 squared times 2 cubed is 2 times 2 times 2 times 2 times 2. If a product of exponents is given by a sum in the exponential, then what should a quotient of exponentials be? What's b to the x divided by b to the y?
B to the x minus 1.
Yeah. And the final rule we know is what's b to the x to the y? So what we're going to do with the next couple minutes, we'll take each of these rules and use them to determine the rules that go up there. That's what we're going to do today. So we'll start with this. We'll start by trying to understand what the log base b of x times y is. So we'll try to compute. Let's see, maybe I'll even judge, do this. We'll get a formula soon. I know people already have a guess for what the formula should be. So what do you want the log of a product to turn into? Any intuition? Okay, cool. Let's just explore and see what happens. So here's the strategy I'll follow. Whatever the log of x times y is, it probably has to do with the log of x and the log of y. That seems reasonable. So I'll just give those two things names. I don't know. I'm not good at coming up with names. Maybe I'll call the log base b of x capital A, the log base b of y capital B. It doesn't matter what the name is. I'll give them names and we'll go with it. Wait, so I only gave them names, but is that an equation which is in logarithmic form? What does it become if you added an exponential? What's the base? Raised to the power equals the thing inside the parentheses. What do you get for y when you rewrite the other one in exponential form? B raised to the capital B? Maybe that makes capital B not a great variable name, but I'm going to stick with it. Y equals b to the power of big B. So that means that x times y is b to the big A times b to the big B. Right, and that's encouraging. Right? We wanted to know about the log of x times y. Now we have a reformulation of x times y. What's b to the A times b to the B? Yeah, that's a... That's a product of exponentials, so that's the sum of the exponents. So maybe I'll just rewrite the whole thing again. xy equals b to the A times b. a plus b. Oh, is this equation an equation in exponential form? What would you get if you rewrote that in logarithmic form? Let's see, you would get log log base b xy equals. Oh, neat. So the log base b of x times y is a plus b. I don't want something in terms of a and b. I want something in terms of x and y. But do I know what a and b are in terms of x and y? What's a? What you said is true, but like, what is a? Because that's what a is. So, oh, neat. Is that exactly one of the formulas we wanted? So the log of a product is the log base b of x plus the log base b of y. Yeah, I'll come back to some reasons that's an important formula in a little bit. So let's talk about like the general strategy we used. So the whole game here was x and y was some numbers. We expected the logs of x and y to be relevant. So we gave them names. We translated over to exponential form. We did some arithmetic algebra with exponentials, which is a setting where we know we can do some algebra. And then we translated back. All of the remaining things on that table have arguments which follow the exact same structure. So there's going to be some less derisive word than repetition. I'm going to say almost the same thing a few times today, but it's slightly different settings. Is it true? Maybe that's true. So let's continue this. So I will get the next two results in a moment. What I want to do first is I want to use the thing. So let's use this, 1, to make some computations, and 2, to actually solve some equations. So here's something that maybe I want to compute. The log base 3 of 2 plus the log base 3 of 1.5. And maybe I'll write these rules as I get them. So there's the rule I have so far. So let's take a look at what I have there. Is that 2 logs added together? So I can use this rule going this way to rewrite it as a single log of a product. So that's the same thing as the log base 3 of 2 multiplied by 1.5. And what is 2 multiplied by 1.5? 3. So this becomes the log base 3 of 3. And what is that? Neato. So even though I couldn't compute on the lows the log base 3 of 2 or the log base 3 of 1.5, I can compute the sum of their logarithms. Let's use this to do some solving. So here's an equation. The log base 3 of x plus the log base 3 of x plus 8 is equal to 2. Let's try to solve that. On the left-hand side, do I see a sum of 2 logs? I do, right? So I can rewrite that as the log of a product. So rewrite the left-hand side as a single logarithm. that'll get me the log, still base 3, of the product now, x multiplied by x plus 8 equals 2.
Everyone with me? All right. So in looking at that equation, if you wanted to solve that equation, what's something that you would want to do? Yeah.
So you would multiply everything together so you get log base 3 of x squared plus 8x equals 2. And then dissolve the log to get the natural equation.
What do you mean dissolve?
I guess like 3 squared equals x squared plus 8x.
Yeah. So you would rewrite it in exponential form. Nice.
So, doing exactly that, you get x squared plus 8x equals 3 to the 2.
I think you probably meant the right thing by dissolve, then.
Yeah, start with words.
That's cool.
One thing that I
And what's 3 squared? 9.
All right, so I get x squared plus 8x minus 9 equals 0.
That looks like an equation that's easy enough to solve? You can factor it. How does it factor? All right, so that's playing the game. Find two things that multiply together to be negative 9. So that'll be a thing and minus a thing. And they need to add together to be 8. 9 and negative 1 do the job.
Oh, equals 0. Okay, cool. So what are the solutions to that equation?
Cool. So I'm going to do one last check because there is a subtlety here. As is, that answer is incorrect. So you nodded your head. Do you see why? Oh, okay. Okay. Let's talk about why. So let's try to plug them in and just write the standard double-checky thing to do.
Let's plug in x equals negative 9, see if we get equality. So that would mean that I want to compute the log base 3 of negative 9 plus the log base 3 negative 9 plus 8. I would like that to equal 2.
Is anything I just wrote upsetting? Can't have negative numbers in a logarithm.
Both of those things are bad. So negative 9 is not in the domain of the original problem.
So, you remember how we've said a few times, like, you check the domain before you do any algebra, because doing algebra can change the domain?
That happened when we replaced this quantity with that quantity.
So x times x plus 8 can be positive when both x and x plus 8 are negative. So this quantity made sense. That quantity does not. So, whenever you do something involving logarithms, like this move in particular, you might accidentally enlarge the domain.
So you have to check if things are in the domain. Maybe I should also check x equals 1. So checking x equals 1, you'll get the log base 3 of 1 plus the log base 3 of 1 plus 8 is 9. Let's see if that's true.
What's the log base 3 of 1?
0. Log of base anything of 1 is 0. What's the log base 3 of 9? 2, right? 3 squared is 9. Oh, hey, yeah, that's 2. That checks out. So it looks like the only solution to this equation is x equals 1.
Nice. People feel pretty good about that so far? Yeah.
What does the function of logarithm look like again?
Do you mean the graph of a logarithm? Yeah. Well, you should have it in your notes. So exponentials look something like that. So logarithms will look something like that. Unless the base is negative, then it'll be like that, but reflected. So let's recall. I could swear we did that. Okay, that would explain it. All right, so there's b to the x when b is bigger than 1. Right, exponentials grow when the base is big. So there's log base b of x when b is bigger than 1. There's an exponential where b is between 0 and 1. It gets small instead of big. Reflect that over the line y equals x. You'll get something that looks like that. Yeah. Cool. All right, so there's what you get out of log of a product. So the log of a product is the sum of the logs. So log turns multiplication into addition. What do you think log will turn division into then? Subtraction, right? I guess some analogy there. Addition is to subtraction as multiplication is to division. So that certainly seems plausible. Let's go ahead and try to get that. We'll follow the exact same logic. Let's give log base b of x and log base b of y names. What names would you want to use for these? It doesn't matter, right? Just pick something. So, if we give these two things names, I now see two equations in logarithmic form that I can rewrite in exponential form. Rewrite that in exponential form. What do you get? Yeah. Cool. And same thing for the other one. Something similar but with b. So that means x divided by y. What would that become now in terms of b's and u's and v's? Well, x is apparently b to the u. Y is b to the v. So what's b to the u divided by b to the v? Sorry. Good, but yeah, I was looking for exponential laws, which I think is what you were going to say too. There's just two. Okay, there are too many voices at the same time. Oh, neat. Okay, so now we have the same situation as before. I see x divided by y is b to the u minus v. Is that an equation in exponential form? We write it in log form. You'll get log base b of x divided by y is u minus v. But then remembering what u and v are, groovy. So, on the one hand, the reason that this thing is true isn't that deep. That's one of the things that I want to point out. You have facts for exponentials. Do some translation to get to exponentials. You can prove things about logs. And we we get that fact about logarithms. We can similarly use that fact in order to do computation and to solve equations. So maybe I'll again give you a choice here of 3 things. Should we spend time doing this computation? All right. So I see at least one head nodding. And the options are, I talk through the computation, you do it, and then we come together. People want me to talk to it before we talk about it? All right. I'll actually put your mask over here. So, let's do it. So the rule I just got is the log of a quotient is the difference between the logs. Right there I see a difference between 2 logs. So I should be able to rewrite subtraction as division inside of the parentheses. Let's do that. And I'll wind up with the log base 5 of 15 over 3. Cool. Is it clear what that's going to work out to be? What is it going to work out to be? Almost. I think you said 0, which isn't quite right. You said 1, then you're perfect. Yeah, this will work out to be 1. Because the log base 5 of 15 over 3 is the log base 5 of 5. Log base b of d is always 1. People feel pretty good about that? Let's use it to solve an equation. Let's solve the equation. Log of x plus 2 minus log of x plus 1 is equal to 3. And I'll give you the choice. Do you want to do the algebra on your own? Or should I keep talking right now? How many people would like me to be quiet for a little bit while they walk? Okay, is there interest in me continuing to talk? All right, I'll continue to talk. Let's try to solve this equation. So there's going to be a very common theme in a lot of these. I'll try to rewrite anything that involves a logarithm in terms of a single logarithm. Then I'll rewrite an exponential form, and then hopefully my life will be better. So I see a difference between 2 logs on the left-hand side. So starting with the left-hand side, we write that as a single log. So that will become the log base 2 of what? Yeah, that's what you were going to say too? Awesome. I mean, I just agreed immediately. I didn't actually think about whether what you said was right, but I think it is. And that's equal to 3. All right. Is that now an equation in logarithmic form? So can I rewrite it without any logs left? Yeah. Just rewrite it in exponential form. I'll get x plus 2 over x plus 1 equals 2 to the power 3. And what is 2 to the power 3? 8. How many people would have put 9 if they hadn't thought for an extra couple seconds? Oh, well, I mean, I think someone here is a liar because that's an easy mistake to make. In that it's a mistake that I was close to making, but fortunately I asked you guys what it was instead of doing it myself. So, x plus 2 over x plus 1 equals 8. There's an equation to solve. What would you want to do to solve it? Multiply the denominator over x plus 2 equals 8 times x plus 1. X plus 2 equals 8x plus 8. All right, keep on going. Subtract x to the other side. 7x. What else should you do? Subtract 8. Negative 6. Divide by 7. X equals negative 6 over 7. All right. So it looks like there is one solution according to this equation.
Say that again, yeah.
Is that possible? Or
There's a reason to be novice.
I was thinking, because if you plug that in, there's still going to be possible.
Let's check if it's actually in the domain of consideration, though you already have done. Let's check if it's a solution. So we will need the log base 2 of negative 6 over 7 plus 2 minus the log base 2 negative 6 over 7 plus 1. Maybe we'll just go so far as checking that the domain is correct. Negative 6 over 7 plus 2. If you wanted to actually write that as a single fraction, what would you do? Okay. So maybe I'll even do that either way, so 10. So 2 is 14 over 7. Similarly, that 1 is 7 over 7. Get the log base 2 of 14 minus 6 is 8/7 minus the log base 2 of 1/7. Is everything in the domain of consideration? So it's at least in the domain. I will now report that as the solution. Yeah.
So where would the limits be? Like, is there a... Because if you can't have the x be less than 1, is there a... There's not an asymptote or anything like that. Does that show up on the graph?
Well, let's do this two ways. I think this is a good use of time. Let's compute the domain of this thing. All right, so we'll look at each ingredient one at a time. So that thing needs to be defined. What numbers am I allowed to see inside of a logarithm? Positive. So that tells me that x has to be bigger than negative 2, right?
Oh, and 0.
Yeah, what's the log of 0? Undefined. Square root of 0 is fine. Log of 0 is bad. There's a vertical asymptote of logarithm. What does that tell me about x? Cool. So let's draw each of those one at a time. There's 0, there's negative 1, there's negative 2. The first one says that anything over here is bad. The second one says that anything over here is bad. And an input will be bad if it's bad for at least one of the two things. So all of these are bad. No, sorry. When it comes to actually using the whiteboard, this room is highly compromised. So if you want to compute domain of a complicated thing, just compute the domain of each ingredient and make sure you can satisfy all of the domain constraints. Cool. So that satisfies the, nope, flip too far. All right, we wanted to get a few formulas. We now have that formula and we've used it. The last one, at least in this table of formulas, is what is the log base b of x to the power y? All right, so the same motivation. So logarithms denote multiplication down to addition. And Well, I don't know about that. You stood up. Scanning for signal. That's interesting. This is back on, so that should come back on. It did. Okay, good. Whew. So logs demote multiplication just down to addition. Exponentiation is iterated multiplication. So logs should demote exponentiation to iterated addition. What's another word for iterated addition? What's 5 plus 5 plus 5 plus 5 7 times? 7 times 5? So exponentiation, maybe that gets demoted to like multiplication. The log base b of x to the y, maybe that's y times the log base b of x. In fact, maybe I'll just say this. It is, by a really similar argument to what we've done already. And let's talk through that same argument. It'll be very much the same. So, I won't do anything with y yet. I'll give a log base b of x a name. Doesn't matter. Give it any name. If I rewrite that in exponential form, I'll get x is b to the power q. And I'm interested in x to the power y, right? So if I want to understand x to the power y, well, that's b to the power q raised to the power y. Do I have any exponential laws that tell me what b to the q to the y is? You multiply the things in the exponent. Yeah, it'll be b to the q times y. Is that an equation in exponential form that I can rewrite in log form? Yeah, let's rewrite it in log form and see what we get. In log form, I'll get log base b of x to the power y. Hey, that's encouraging. I was interested in log base b of x to the power y is equal to q times y. And what was q again? Great. Times y, right, because there's a times there, so that should still be times. Nice. So that means, oh, well, I screwed up earlier. Log base b of x to the y is y times the log base b of x. Flipping back to the formulas we wanted, log base b of x to the y is y times the log base b of x. And those formulas are going to be important through much of the rest of the semester. We will use those an awful lot. So we can use all of these things together to solve more complicated equations. And maybe this is one that I won't go through all the way, but there's an equation. Let's follow the same basic strategy we did with the previous two solve this equation examples to solve this. Let's try to write the complicated side as log of a thing, and then we'll get it into exponential form and get an equation which will hopefully be simpler. So let's try to do that. And let's start with this piece. What's 2 times log base 5 of x plus 1? What can we do to that? Yeah, this will become log base 5 of x plus 1, parentheses matter, squared. And then the rest of it I'll just carry along. Minus log base 5 of x minus 1 equals 2. All right. Yeah.
This is the closest one, so it should be log 5. And it would be x plus 1 squared over x minus 1.
Yeah, so there's a thing that can just, yeah, there's that. All right. What should I do next? Yeah, we write it without a logarithm, put it in exponential form. X plus 1 quantity squared divided by x minus 1 is the base is 5, 5 to the power 2, which is 25. And all right, so I'm getting to the point in this example where, well, so here's a question first. Does that equation look like an equation that is easier to solve than the one you started with? Yes. Does that look like an equation that you know how to solve? Does that look like an equation that we should spend more class time to solve? You want to see the algebra finish? All right, so you'll go through, you can get that down to maybe 2 x values, get some number of solutions, check if those solutions actually work, and that they're in the relevant domain. But I won't do that. I'll leave that to you. All right, so the last thing that I want to do is I want to get a thing that I alluded to last time, namely some of the change of basis formulas. So here's a statement right here. So there's, if you like, just this rule written down with different variable names. The log base b of a to the x is x times the log base b of a. On the left-hand side of that, is that an equation that's in logarithmic form? Yeah, in maybe 2 different ways, but in particular, thinking of that as the logarithm. If you rewrite that in exponential form, you'll get a to the x equals b raised to the x times the log base b of a. Oh, neat. So, what does that mean? What's one way of interpreting what this means? This means that if you feel okay about logarithms, then there's really only one exponential. If you know what b to the x is, then any other exponential will just be done by that formula. For any exponential, a to the x, for any base a and your favorite base b, a to the x is the same as b to the power x times the log base b of a. So a to the x is b to the x after being compressed, possibly stretched, by a factor horizontally, by a factor of log base b of a. So all exponentials look the same. They're just either compressed or stretched, or maybe reflected. Neat. So there's the first change of basis formula. And you can use that to do some things. If you want to write 2 to the x as an exponent with base 3, you'll say, well, 2 to the x is equal to 3 to the power x times the log base 3 of 2. How does that feel? Does that feel nice enough? And so that might be a less exciting change of basis formula than the one that we're about to get, because chances are your calculator just has like an up caret button that you use if you want to compute exponentials. Yeah, let's go down here. Let's get the same thing, but in the language, but for logarithms. So here is a fact about exponentials. Well, exponentials and logs undo each other. They're inverse functions. A to the log base a of x is always equal to x. So there's an equation. Let's see what happens if we apply log base b to both sides. We will get the log base b of a to the log base a of x is equal to the log base b of x. So let's try to simplify and just muck around with that a little bit. In particular, let's try to solve it for the log base a of x. So let's look at that and see what we can get. In there, do I see an exponential inside of a logarithm? I mean, I do, right? It's log base b of a to a power. I have a rule that can help me simplify that. Using logarithm laws, I'll get that this gives me the log base a of x times the log base b of x, log base b of a, equals log base b of x. If you wanted to solve that for the thing in blue, what would you do? Well, for all of the things look complicated, but thing in blue that you want to know what it is, times a number is equal to a number. Divide by this number. And we'll get log base a of x equals log base b of x divided by the log base b of a. So here's the big fancy fact that we've mentioned a few times. Pick your favorite base b. If you're a calculator, then chances are that favorite base is 10 for some reason. Any logarithm can be expressed in terms of log base b by the formula log base a of x is the log base b of x divided by the log base b of a. So if you wanted to understand the log base 3 of x, your calculator can only compute log base 10 of x. You can compute log base 3 of x. So, what we just did waxed a little bit abstract sounding. I get that. Let's focus on the takeaway. Oh, well, you can't actually read the bottom of the screen. So you have a favorite base that you like to work with. Maybe that base is 10. If you understand logarithms base 10, I claim you understand logarithms with like absolutely every base. The reason that that's true is because the logarithm with respect to a base that you don't like is equal to a quotient of the logarithm with respect to a base you do like, divided by the logarithm with respect to a base you do like. If you want to compute the log base 3 of x and your calculator only walks base 10, log base 3 of x is the log base 10 of x divided by the log base 10 of 3. That fact seem reasonable? People feel? Okay, so let's see this in action. Here's an application of that fact. So your handheld calculator, how many people, as far as I know, their handheld calculator can compute logarithms, but only with respect to base 10? With only base 10. Okay, at least a few hands went up. Here is a calculator that can only compute logarithms base 10, the Google calculator. If you ask it for the log base 3 of 2, it doesn't know what to do. If you ask it for the log of 2, it'll give you something. It'll give you the log base 10 of 2. And that means if I wanted to compute the log base 3 of 5, Google Calculator won't help me. But it will if I know that rule, because I know that the log base 3 of 5 is the log base 10 of 5 divided by the log base 10 of 30. So if your calculator only walks base 10 and you want to compute base 30, compute the log of 5 divided by the log of 30. How do people feel about that? That fact seem useful? Nice. That's the takeaway of what just happened. Groovy. So let's talk about where we're going to go from here. Yeah, okay, yeah, we can do this. So let's go ahead and try to, I have just that amount. Okay. So the log base 3 of x, if you wanted to compute it in terms of log base 10, that is the log base 10 of x divided by the log base 10 of 3. So, using a computer, log of 3 is somewhere around 4.8. Point 48? All right. Well, what does division by 0.48, what will that do to a graph? It will, yes, stretch it by a factor of approximately 2. Stretched by a factor of 1 over 0.48, which is approximately 2. Right, 0.48 is somewhere around a half. So what that says, well, all right, so let's actually address the prompt. So let's use that fact. Here are two graphs. They both look like logarithmic graphs, right? Based on the fact that's just been written, the log base 3 of x is the log base 10 of x stretched vertically by a factor of about 2. Which of those is log base 3 of x and which one is log base 10? Yeah. If you take that, stretch it by a factor of about 2, you get the blue one. That's consistent with that fact. Groovy. So, I'll stop there. Maybe I'll suggest you think about this last computation, log base 3 of 2 times the log base 2 of 3. Work out what that is in terms of the change of basis formula. And I'll see you all again tomorrow, I guess.